When we're looking at a particular reaction and gathering experimental data from it with regard to rate, we'll be able to come up with a mathematical expression called a rate law. Generally speaking, rate laws would be equal to, or rather would be as an equation, the rate equal to a constant times each of your reactants raised to a particular power. So for this set of reactants, we have our two reactants, hydrogen and iodine. Our rate law would be an equation that describes how the rate will change with concentration. And so we have K here, which is a rate constant. And we're going to see that rate constants are depend on temperature. Generally speaking, as temperature goes up, your rate constant also goes up. We also have, as part of this equation, the concentrations of our reactants raised to coefficients. We'll see what those coefficients will be when we look at some data. These are concentrations of reactants are raised to powers. One thing to note is that rate laws are always experimental, or we can say experimentally derived. We can't just come up with a rate law by looking at an equation. Although, that said, there may be some general guidelines of what rate laws typically look like, although we must always remember that they have to be experimentally derived. We may look at an equation and be able to come up with a rate law, but that may or may not be the correct rate law. Rate laws can only be determined from experiments, and that means data. So, just like before, I have a magic amount of data for us. You may want to pause the video to copy down these numbers. So we have 6 experiments that were conducted. We have concentrations of hydrogen and iodine at the start of the reaction, and we have some initial rates that were measured. And so we can see here, in the first 3 experiments, our iodine concentration is unchanged, but our hydrogen concentration is increasing. We see for example, between experiments 1 and 2, our concentration of hydrogen doubles. And if we look at the rate, our rate has also doubled, which tells us that we have some information about the rate of reaction here. What we'll do for this is we have to remember that the rate is always K times reactant 1 raised to a particular power times reactant 2, or however many reactants you have, all raised to their power. So if we're comparing 2 separate ones, well, we can say, okay, well, if the rate at one experiment was a particular value, we can compare it to the rate at a second value to determine the rate law of the reaction. We'll see what those coefficients are going to be. And how we'll do that is we'll say, okay, well, since we know this, we know that the rate for experiment 1 will be our rate constant. That doesn't change, only changes with temperature, which is not something we're really going to look at until the end of the chapter, times our concentration of hydrogen times the concentration of iodine, all for experiment 1. And we're going to see if we're going to compare it. We have our second experiment. All of our values here. Notice that the K's are in both. If we're going to divide them, I forgot my fraction there. The k's will cancel out, they're constant, right? So we're really looking at the change in rate and the change in concentrations. So if you plug in the numbers, the rate for experiment 1 is 5.4 times 10 to the negative 7. Our concentration of hydrogen is 0.01 raised to the n power times 200 to the n power. Again, these are placeholders so that we figure out our coefficients. Our second rate was 10.8 times 10 to the negative 7 from the data table. We're going to see that our second hydrogen was 0.02 times 0.2 to the n. Notice that since our iodine is the same in both experiments, that gets canceled out. Right? 0.2 to the n power over 0.2 to the n power is just 1. So really, we have 1 over 2, if we just simplify that fraction, 5.04 over 10.8, is equal to 1 to the m power over 2 to the n power, or 1/2 to the m power. And so if we solve for m, 1/2 equals half to the m power, m has to be what? Right? Ta-da! Generally speaking, these coefficients are small whole numbers. So if we go ahead and do the same thing for iodine, if you do the same process for iodine, we're going to see that for iodine, n is 1. If you go ahead and do the calculation, you'll see that n is 1. And as a result, that means that the rate for this reaction is equal to the constant times the concentration of hydrogen times the concentration of iodine, both to the first power. And while that may not seem particularly exciting right now, it will be very useful when we talk about mechanisms of reactions. And so I'm going to conclude this video by giving a general statement, but again, under the proviso that rate laws are always experimentally derived. You cannot you cannot look at the chemical equation and always get your rate law out. That said, for an equation, say we have our favorite equation from before. Generally speaking, the rate of this reaction will be a constant times a to the a power times b to the b power. This is a general statement here. Again, notice we're only including the reactants in this. We're not going to include the products. Our rate law is equal to the rate constant times the concentration of A raised to its coefficient and the concentration of B raised to its coefficient. This is true for any equation. However, as we saw with Hess's law way back in Gen Chem 1, that reactions can be combined, right? We saw that if we take two reactions, we can put them together to make an overall reaction. And so, unfortunately, we see that we really care about rate laws for individual steps. We don't care about rate laws for overall reactions. And so, if our reaction happens to be an overall reaction, this rate law is useless. So that's why you always have to take this information right here with a grain of salt, because rate laws must always be experimentally determined. We cannot just look at the equation and come up with it directly. For any equation, this is true so long as that equation is not multiple steps. If everything is happening in just one step, then this rule applies. However, again, with Hess's law, we remember that sometimes reactions are multiple steps. And in that case, we need to look at those steps individually, not looking at the overall reaction. One last thing here. M and N, those coefficients that we had, those were the exponents, tell us the order of the reaction. So if we take our previous example, we saw that the rate was equal to K times H2 times I2, both of which were 1. We would say that this reaction, I'm going to put the 1s here even though we don't normally put coefficients of 1, that this reaction is first order in hydrogen. So it's going to obey what are called first order kinetics when we look at hydrogen. That's something we'll talk about in our next video. We'll also say that the reaction is first order in iodine, because iodine's concentration is, exponent is 1. So we have order in respect to each reactant, and in this case they're both first order with respect to each reactant. Overall, the reaction is second order, because we have M was 1, N was 1, M plus N is 2. So our overall reaction is considered second order, but the reaction is first order in respect to hydrogen and also first order in respect to iodine. We'll see that this will not always be the case. We can have second order overall reactions that are not made of first order reaction components. And we'll see that again in next videos.